I want to finish up I2C. Well, I shouldn't say finish up. I may lecture on it again next week, but I want to get us ready to actually try Project 3 a little bit. And you may have questions in the lab, of course. I understand. But again, we got our 28379D processor on the launch pad, and it's the master. We're going to set it up as the master for the I2C, and it's got our SDA and SCL lines. CL, come on, Dan. All right, and then remember, we could tie that to a bunch of devices, couldn't we? And each of these have an SDA and an SCL line. And you could put quite a number of these devices on your board, right? And talk to all of them. You just daisy chain those wires to all the devices, and now you have a way to communicate with all these guys. Right? There could be more than 3 chips, right? We said there could be 127. I think that would be crazy. But anyway, technically we could do that, I guess. If we could find 127 chips that have different addresses, that would be the challenge there. Anyway, okay, now what we talked about is there's this protocol that they came up with, right? Whoever, I think Philips was the first company, I think, that put together this I2C protocol. And the idea, remember, was to first send over an address and then telling it, I want to read or write data to you. Remember, we can only do one at a time. We can either read data or we can write data across the I2C. Okay? So you would have to decide. And for many chips, that's okay. A lot of chips, right, you, especially sensor chips, and that's what this is used for a lot, you initially just set it up. So you write data to the registers saying how you want this chip to act, how often you want data or whatever, right? All these settings. And then after that, you're just simply reading it all the time, right? Because you're just getting the information. So a lot of times that's not really a big deal. But now, if you had an I2C chip that, you know, well, I don't know if I've ever seen one, but like a RAM chip with over I2C that you have to write out data and read data constantly back and forth, is probably what, and that's probably why we don't see those. This wouldn't be the best serial port for that. Okay. Anyway, so, and then what was that protocol? And I want to get you through the code that I give you for Project 3. So let's look here. Where do I went back to MATLAB? And here was our very simple one. In this case, we were just, the protocol here is I just want to start reading from this device. This one here doesn't really have the idea that there's registers over on the I2C device. It's just saying, okay, I want to start reading data that you have sitting for me and sitting there. So I send the address and I say I want to read data, and then you read back byte 1, byte 2, byte 3, back and forth. So that could be possible. You could set up, you know, there's an I2C driver for the Raspberry Pi. You could have like our the DAN 28027 chip, for example, or you could reprogram that so that whenever you ask to read that chip, it knows exactly what to send you. And it sends you those 3 bytes every time. What I'm trying to get at is there's another way that most of the time you use I2C, and that is, and this is what I talked about right at the end, most of the time with sensors that you read the data sheet for, the timing diagram is going to look like this instead for read. And let me look at that. So here we go. And get the plot. Most of the time, we have this, when we're reading data from a device, we have to send over the slave address twice. Okay? Because what we need to tell the device, and remember, this device over here has a list of registers, and they're numbered. Right? Register 0, register 1, register 2. And remember, this is over on the device that we're talking to. So the first thing you need to send to the device, so notice we're doing an address and then the write command. You're writing to the device the register you want to start reading from. Okay? We showed you this example last time, and we'll look at our 2 chips that we're using for the project, but last time I showed you, if it's still here, this other chip from Microchip. It's called the MCP23SO8, whatever. We don't really even know what these are, but these, these IO direction, IO polarity or something, these registers right here are labeled 0 through A. You may not want to read all of these every time. Maybe you just want to read 2 of these or 4 of these, whatever. So the first thing that the I2C protocol, when you're reading these registers, needs is which one do we want to start reading at, right? And then if we ask for 8 bits, it'll give us this value. And then if we ask for another 8 bits, it'll give us the value of this register, and so on, right? And it's always an 8-bit chunk all the time from I2C. We always read 8 bits. Okay, and so that's exactly what this timing diagram is showing us here. There, I'm saying I want to read starting at register 2. Or not. Then I reissue the start command and the address and say, now I want to read. Okay? And then what comes back is the value that happens to be in register 2. That's the first byte. What's the value here? This is the value sitting in register what? This is 2. What's sitting in register 3, 4, 5. See how that works? Okay, good. So now you can do more than 4. We're going to find, when we talk to the BQ32000, our real-time clock chip, it's keeping track of time. We need to read from that what is the current seconds of our time, right? We want to get from that it's Wednesday, October 20th, whatever, 9/13 at X number of seconds, right? That's where we're going to read from that chip. Okay? Well, you'll have to go and read the seconds. That's going to be one 8-bit value. And we'll show you this. We'll show you the timing diagram. And then the next one is probably, seconds, minutes. The next 8 bits is the minutes value. The next 8 bits is the hours value. You see what we're doing? And in that case, what do we need? We need seconds, minutes, hours, day, year, I don't know, we'll look at it. We'll look at all the registers, right? So it's more than 4 in that case to get the current date and time from our little chip. The watch, I always call it, right? The thing keeping track of time for us. Even when we have a battery in there, when we turn off power, it's still keeping track of time. Okay, so that's that. So that's this idea of reading a device. Now, writing is a little bit, I don't know about easier, but it's a little bit different in that we don't have to issue another slave address. Okay, so what does that look like? Let's run that. Right here, run. So to tell an I2C device what register we want to write to, notice we just have to issue a slave address, send out the slave address, say we're writing, and now the difference is the first thing we write is the register we want to send this data to. Okay? And so in this case, we want to write to register 6. What do we want to write to register 6? The next value we send across. Okay? Then the next, it automatically increments to register 7. Whatever that is inside the I2C chip. 8 and 9 would all go across. So by issuing that command, we've written data to 4 registers, 4 8-bit registers inside the I2C chip that we're using. Okay? Now again, this is not always, though you have to read the data sheet, but the chips we're working with in lab today, and most chips you work with at I2C, have this type of protocol for writing to the device. Okay? I can't say everyone does, but a lot of them come with this format. So again, you can write more than 4 bytes across, and we're going to need to do that when we write to the BQ32000. You're going to create a function that is set date and time or something like that, right? And again, you'll have to send over, when you write to it, you're setting the new time and new day for your real-time clock chip. You'll set the minute, the seconds, minutes, hours, day, year, all that kind of stuff. You'll write over in one big long write of, I think it's 7 things. Okay, so you'd write to the register that you're going to start at, which the seconds register is 0. So you'll just say write 0, and then you'll write 8 bits what the seconds is, what the minutes are, bloom, 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 across. Okay? Good. All right, so let's look at the data sheet real quick. And let's go. Do I have it up here? Okay. Dan, here we go. I2C. So, what do I got in this thing? All right, just go over the pins. And then, again, just describing the pins. You can look at that. And then here's my registers. I have on register 0 that we can read or write. Well, let's see. You could write to this, but it would just not do anything. This is an ADC reading, so that's just something you would read. If you would write to it, nothing would happen. You could write over to address 0 on the DAN 28027, but it just wouldn't do anything. It would take that data and put it nowhere because there's no register to write to. It's just a read from register. That's why I say read only here. But doesn't mean you can't write to it, and things wouldn't blow up or something like that, but just nothing happens. And then, so registers 0, 1, 2, 3, and then registers 4, 5, 6, 7 are the value that we're going to drive output PWM values. And in this case, it's going to be an RC servo pulse like we've done before. 50 hertz square wave with the outputs like 4% to 12% duty cycle like we did in lab 3, was it? Or lab 2, whatever it was. And so you'll be scoping the PWM signal like that once you talk to this chip over I2C. So you've got these registers that you can think about I need to communicate with, right? When that's going to be your whole point. We're not going to get, in Project 3, we're not going to get into all the 1s and 0s that we need to set the registers to make the I2C do what we're talking about. What I'm talking about is I'm giving you all the code for the I2C peripheral on the 28379D. Your job is just to read the data sheet and figure out what data needs to be sent when and what data needs to be received when, okay? And we'll keep on. You'll be reading through that. I think the project does a pretty good job of explaining that, and then you'll ask some questions. Okay? All right. And then the timing diagram here, very similar to what I was just showing you there, but let's see here, to write to the RC servo commands, you would need to set its address is 25, which is hex 7D is just what I chose. Okay, the address 7D, and then you would say you would write, and the only thing that really makes sense is to write starting at register 4. Remember, because those other registers were read only. So you'd start at register 4, and then you'd write the 2 bytes of our RC servo command. Our RC servo command is going to be a value, I think it is, you double check it in the data sheet. I believe it's a value from 1500 to 4500. We can even just look real quick. It's right here. Let me, that way I don't misspeak. Right here. It is a value Yeah, you got it right. Between 1500 and 4500, where 1500 is 4% duty cycle and 4500 is 12% duty cycle, right? Approximately minus 90 to 90, like we talked about with those RC servos. Okay? And so that number, 1500, 4500, is a number greater than 255, isn't it? 255 is the biggest number we can send over in 8 bits. So we need to send a least significant 8 bits and a most significant 8 bits. And then the DAN 28027 will put those two together to figure out what that number is between 1500 and 4500. Does that make sense? Okay? So because I2C only communicates 8-bit chunks at a time, we have that issue that we have to divide bits and all this kind of stuff. All right, let's look at the code that's given for that. So that is in our project. In project 3, I give you code to cut and paste. Where is the project? Not up, of course. All right, let's go find it. I guess I'll find it online. Here it is. I did have it online. Okay. This is lab 5. Sorry. Let's get it. COECSL. Go to ME461 and project 3. Okay. So go down here. Let's zoom in a little bit. This code now, we're going to put these functions that we write right here. So you're going to write 4 functions for me, and I give you a lot of the code. Write DAN 28027 RC servo. Read DAN 28027, the 2 ADC values. And then we're going to write to the BQ32000. What we're going to write? The second value, the minute, the hour, the day, the date, the month, and the year. Okay? And you'll only call that once, won't you? Right? You don't want to set that continuously, do you? Because then time will just be whatever you constantly set it to. So you'll set that maybe up in main, and yeah, anyway. And then read BQ32000. Every so often we want to go and read the second, the minute, the hour, the day, etc. Okay? So you're going to be creating those functions for me. Now, I don't give you exactly those functions, but I give you a pretty good, darn good start. There's the initialization you're going to call for the I2C. And by the way, if you do want to get down into the registers of this, there are some things I'd love to play around with in final projects with the I2C to do some better error checking than I do and all that kind of stuff. So if this is something interesting to you, talk to me. We could do a little bit better with this code. Anyway, okay, so here's this function, write 2 16-bit values to chip XYZ, okay? You're going to modify this a little bit to talk to the DAN 28027. But notice what I do first. I've got these 2 16-bit values, right, that I need to convert to 8-bit values. The least significant, right, which I just AND with FF, right, to give me just the bottom 8 bits. And then the most significant, which, look, I'm right shifting by 8 and ANDing with FF. Got that? So anyway, so we got those 8-bit values. Now, look what we do. Okay, so a little bit of, again, checking if somebody else is using the I2C. Is it busy? Okay, and usually the only time it's busy on us, the way we're using it, is right at the first, right when you first initialize this I2C is the only time I usually find that, but it's good to check for it. And then we're saying, what address do we want to talk to? Now, for the DAN 28027, it's a different address. Here, ChipYXYZ has the address of hex 25. I just pulled that out of the air. We're going to send 5 things. And what are we going to send first? The address, the register we want to write to first, register 4. Okay? You'll look through this a little bit more. Then this sets up, this crazy number here, sets up the I2C serial port to issue the start command and send over the address. There's a bunch of 1s and 0s in that register that set up the I2C. Tell it to do that. Again, we're kind of glossing over that for this. You're just going to use this code. And then we sit here and wait until the I2C, in other words, it's sent out the start condition and the address. And actually also the byte 4. Sorry, the byte that is 4, the register. So when we're ready, then it knows we've done all that transmission across, we've received an acknowledgement also, and now we're ready to send over the least significant byte. This part, right? So we've gotten this code, has gotten through this, it sent register 4 instead of 6, sent the address, it sent the register, and now we're to the point where we need to send the first data byte. Okay? Whatever that is according to the data sheet. And we come back here, and that's what we do. So we send across the, where's it at? Right here, the command least significant byte. That happens to be your protocol. If you look at your chip, it may be most significant 8 bits first. You got to look at the data sheet, see which one it is. Okay? And then we wait again until that's been transmitted. Then we send over the command 1 most significant byte. Wait until that's done. Command least significant byte. And then, of course, command 2 most significant byte. And then return from this function. Okay? That everything was okay. That we made it through. So that issues, that code right there issues this, what am I doing? That code right there issues the stuff in MATLAB here, all these commands. Okay? This last little bit right down here at the end is actually, by setting this, where is it at? Somewhere here we issue, oh no, that's right. When the count reaches, see we set count to 5 up here, right here. When count, every time we send out 8 bits, that count gets decremented. Whenever that count decrements to 0, the stop condition occurs. Okay, so that's how it knows when everything's done, by counting through that count. But again, well, yeah, you will have to adjust that, right? If you want to send across more than 5 bytes, you'll need to change that when we get to the BQ32000 chip, for example. Okay, so that's the number of bytes we want to send across. Now the code for the read cycle, let's pull up that again. All right, sorry, let's go run it. So for the read, it's a little more, not much, but a little more complicated. We got to issue these 2 start commands, don't we? So now this is what we're trying to produce in our code, okay? So we're first going to see, we're going to send a command, a write command with a count of 1. All right, so if we go back to our code, you're going to cut and paste. Okay, so now we're going to read. So the first thing we do, which is a little counterintuitive, but the first thing we got to do is write. So this is what, and this guy is writing to register 10 first. So in other words, see this code, you got to get the right register, slave address, you got to get the right register you're talking to, but we're just sending over one thing. And you can see with my comments, this puts it in master mode, and we're transmitting with the start. We're also not issuing a stop with this command, all these 1s and 0s in this mode register, the I2C mode register. Okay, and so when we wait for that to all be done, and then we're ready to, let's see here, yeah, count 1, and we're ready to send over, no, sorry, wait a second. Did I misspoke here? Was there another thing up here? No, okay, fine. So we issue that, and then we have to reissue, that's where it is, right here. We have to reissue this another start with address again. See how I set address, and then I set the count that we're going to read, the number of things we're going to read. Again, that may, the address you'll need to change, the count you'll need to change for the number of things you're reading. And then we reissue that start and read command. Okay, and that goes, and then we wait for that to be ready. And then what do? When everything's ready, that means data has been pulled in, and we can go read the receive register. And that goes into the value least significant byte. Again, it could be most significant byte for your chip that you're talking to. Then we read the most significant byte, least and then most. Wait again for it to be ready, and then we read the least significant of value 2, and the most significant value 2. And then really important, look what we do. What do we return? We return a 16-bit value that is taking those two 8-bit chunks and putting them together. Does that make sense how we're putting those together, right? Left shifting one of them by 8 and then ORing it with the least significant byte. So that throwing the most significant byte up 8 bits and ORing that with the least significant 8 bits. Put those together and now you got your 16-bit ADC value or whatever we're reading. Okay? The one thing to know with the real-time clock chip, the BQ32000, that's one nice thing about it. There is no 16-bit data in that chip. You can store your seconds value in just 8 bits. You can store your minutes value in just 8 bits. So one thing that'll be different about your code when you get to the BQ3. Now the DAN 28027 does, because it's an ADC reading. That's a value between 0 and 4095. So there will be a 16-bit value there. With the BQ32000, everything's 8 bits. And so then you can just return, it's a weird setting, how they organize the bits, you'll see what I mean by that. And we'll maybe talk about that on Monday, but you may see it as you get to it. How they have seconds stored in that 8 bits of registers is a little weird. And anyway, yeah, you'll see that. So, but you will not, in your BQ32000 functions, be putting together two 8-bit values. You won't need to do that. Okay? Anyway, that's something to think about as you get to that. Okay, again, one, I don't have a huge amount of time. I want to get to the next thing. I also want to leave this a little vague because I want you learning by reading the data sheet too. Okay? But of course, we're there for questions. So ask questions as you do in lab, as you have them. We may talk about this a little bit more next week also to clarify some things that you have as I see you guys working through the labs. Okay, so that's where I want to stop today for I2C.